first of all, you might have seen that your quiz grade from Chapter 1 has been posted on Canvas. I can't give it back to you today because the people that were absent that week have until the end of the day today to make it up in the testing center. But if you want, I can show it to you during office hours, or you can wait and I'll be giving it back on Monday. All right, so I can't distribute it back today because again, those people have an opportunity to make it up by the end of the day. But if you want to come to office hours, I have office hours from 10 to 11, like right up there. You can come and see what you did wrong. And again, I'll be passing it back on Monday, okay? There are 20 points like available in the quiz, but it was scored out of, I think, 16. And that's typically how I will do things in terms of there's like extra credit points built in. Because like silly mistakes here and there, that just kind of happens or whatever, right? Perfection's really, really hard. But nonetheless, if you completely don't understand a concept, then you end up just like not getting any of the points, right? You don't get just nickel and dimed here and there. So there were definitely some people who did great, and then there were like, some people that got their clocks cleaned quite frankly. Which, on the one hand I get. Like, look, I understand that none of y'all are going on to be chemists, right? Nobody in this room is a chemistry major. That's not how it works. Y'all also got to understand that I am here to teach you chemistry, right? Like, I don't pick the topics. The state of California, CSU Fresno negotiates this course outline, a record that I have to teach you. And so that's what we're here to learn. And I understand it's a little weird because everybody's like, why the hell do I have to know E and Z nomenclature? That is not going to be something I'm going to be doing in my future career. But of course, that is what we're here to do, right? Like, it is what it is. So, look, bottom line is I get that, like, I also understand that the topic is not easy, right? So, like, I totally get that. But nonetheless, that is what we're here to do. So I will have an opportunity to make up points on that quiz with what's going to be, how I'm going to have to do it is sort of like with the built-in Canvas quiz. We don't have enough time to be doing too many of these in-person type quizzes because they just eat up way too much time. So I'm going to build some stuff into Canvas that will help you practice that, and similar for chapters 2 and 3, so you can see kind of that paper version of what you would have been practicing skills-wise in lecture, as well as with OWL, okay? So I know that the OWL system might not be everybody's favorite thing in the world, but it is really good practice, right? I mean, the one really nice thing about OWL is that it will generate new questions over and over and over again for you to sit there and practice, right? So you don't want to treat it like a quiz where your goal is to get it right the first time, or if you get it right and you don't understand why, you're like, whew, thank God that's over with. No, the whole point is you're supposed to sit there and play with it until you actually get the concept down, right? And you can do it as many times as you need to. It's there to just generate new problems over and over again. I will be the first to admit that with the chapter 1 stuff, there were a few in there that I would have taken out on retrospect. The formal charge one, we don't need to worry about calculating formal charges of borons and structures. Again, we kind of narrowed it down to those 3 elements that we really care about, like the nitrogen, the oxygen, the carbon, right? So those, we had these simple rules boiled down to. The resonance structure one threw in way more difficult ones than I would expect you to know, okay? So there are a few in there, and I've actually made a short list from chapter 1 of the things that you can ignore and the things that you can focus on that I'll post. But for 2 and 3, I've really made a point to make sure that everything in there, we've gone over examples in class of exactly that, right? And so, the nice thing about that being is that if you're stuck, I can sort of say, first of all, always reach out to me if you're stuck, right? I'm more than happy to help. Oftentimes, I can kind of see what you're doing, take a screenshot. I can often see what you're doing wrong and be like, okay, you're doing this, you need to be doing this. Oftentimes, there's a quick fix. If not, I can always point you to where in the lecture video these examples were gone over. And then worst case scenario, we can get on Zoom and do a few examples, all right? I know that y'all come from this research institution school. A lot of your professors are actually, their main job is research. And so sometimes, I've worked with people who are research professors who are not always hospitable to students coming to them with questions. I was a full-time researcher for a long time. I got out of the research game to get into teaching because I really enjoy teaching. This is what I'm doing, right? So if you have questions, I'm more than happy to answer them for you. It's so pointless to sit there and spin your wheels on these assignments and not know what's going on. Shoot me an email, let's work it out, right? I know that some people, especially the introverted type, would love to be able to go through an entire semester without having a conversation with their instructor, but oftentimes that's the best way to figure something out real quick, right? So anyways, if you are stuck, just please reach out, all right? And again, I can point you to the lecture video exactly where we did this problem. I can try to explain what I see you're doing wrong, or we could just hop on Zoom real quick and do some example problems or something like that, okay? But that quiz is a great summary of exactly what I expect you to know from the Chapter 1 type material. Okay, so I'm gonna make my expectations to y'all very, very clear so that when it comes to exam time, nobody's surprised. The course is gonna be hard enough with me spelling out exactly what I want from you. Okay, but again, that quiz was a good example from Chapter 1, and I'm gonna do the same thing, put together the same sort of thing from the other 2 chapters. Okay? All right, so now we gotta keep going here. Any questions on that real quick? All right, so let's keep going here. We started talking about reactions of these particular functional groups. These are alkenes. We've gone over 2 so far, but let me just point out the general strategy for how you're gonna predict products here is gonna be the same for all the reactions of alkenes, right? You got your starting molecule here. You're gonna get rid of that double bond, all right, because they're all gonna be addition reactions. So we're gonna be adding something to that carbon and to that carbon, adding something to either side of that double bond. So we're just gonna go ahead and get rid of this, draw single bonds on every carbon, not every carbon, I'm sorry, on both of those carbons. And for every single reaction of alkenes, that's exactly the starting point. The question is, what are we putting on either side here, right? That's the difference between these reactions. So we learned about 2 thus far. So let's see if we can't remember. For HBr, what are we adding? What are the 2 elements that we're going to be adding to either side of this double bond? It's kind of spelled out in the reagent there, H and Br, right? The one tricky thing about this is it was that Markovnikov reaction, which meant that the bromine is necessarily going to go on that more highly substituted carbon. All right, so the hydrogen goes on the less highly substituted carbon. Okay, but again, to predict the products, the first thing I do is just draw single bonds on those carbons on either side of the double bond. And then Br2, my 2 things that I'm going to be adding, again, nicely kind of spelled out in the reagents, are just 2 bromines. Okay, and to remind everybody, like the language that I'm using here, our starting thing is the substrate. What we add is the reagent, and what we get on the other side is the product. Okay, and what I told you was the type of questions that you can expect to see on this. I'm not going to expect everybody to have all the different reagents memorized, but I will be asking you for products. So something that you would see on an exam would be, oh, no, I just made it ugly with these other lines, hold up. Would be something like this, right? Fill in the missing thing here. That's pretending to be a question mark. All right, I'll give you a substrate, I'll give you the reagent, you got to tell me what the product of that reaction is going to be. All right, so let's work on that real quick, just reviewing what the 2 reactions that we did. Given this substrate here, give me the product of these 2 reactions. All right, and let me just say, one of the best ways to make sure that you haven't made a stupid mistake is to count carbons. Count carbons on your substrates, count carbons on your products. You should have the same number, right? Leaving off a carbon, adding an extra carbon is something that's really easy to do. Go back and count your carbons to make sure you haven't made a stupid mistake. All right, so again, for each of these, I'm just going to take my starting substrate. I'm going to get rid, whoops, that's huge. Get rid of that double bond and put single bonds in its place. For the reaction with HBr, where am I going to put my bromine? On the orange carbon or the green carbon? The orange, necessarily the more highly substituted one, right? We called that fancy Russian Markovnikov. And so the hydrogen goes on the other side there. Because these are bond line structures, right, the hydrogens are implied, and so if you just gave me that'd be okay too. I'm going to explicitly draw on those hydrogens so it's really evident where that other atom went, but this is also a perfectly correct bond line structure, right, with implied hydrogens. Cool, so same thing on the other side, right? I'm just going to take my starting molecule, I'm going to get rid of that double bond, put single bonds on either side. And then with Br2, we don't have that Markovnikov consideration here because we're just adding the same thing to both of them. So that would be it. Okay? Again, making sure, so like one of the things that you might even see me doing in lecture as I'm doing this is I'll just real quickly go boom, 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 just to make sure I have the correct number of carbons, because that's one of the easiest mistakes to make, to actually accidentally put down an extra line or leave off a line, right? So again, counting carbons is just a good way to double check. So then there was one more thing I told you that I could ask you about these reactions, and that is the intermediates that we would expect to see. Okay, so just quickly to go over that. For the HBr reaction, the intermediates, they kind of help explain a little bit about why the reaction works the way it does. In this case, this intermediate, which is what we call a carbocation, explains why the bromine goes on that more highly substituted carbon. Okay? I have sort of like two choices here. I could either put the positive charge on that side or this side, right? Let's just keep my color coding consistent here. Okay? And remember, we said that the bromine goes on the more highly substituted carbon. And that's because the carbocation likes to form on the more highly substituted carbon. This is more stable. Because it's a tertiary carbocation. This one's less stable because it's a primary carbocation. All right, so in the same way we had these trends in our radical stability where the worst one was primary, or actually methyl, then primary, then secondary, and then the most stable was tertiary, we see the same trend with our carbocations. And so this explains why the bromine goes onto that more highly substituted carbon. Because in the last step of my mechanism here, the bromide ion is going to go attack that positive charge. And that's what takes me to my product. Okay, so the intermediate for this reaction was the carbocation. So on the one hand, the Br2 reaction is a little bit easier to predict products for. But on the other hand, the intermediate looks way worse, right? It's much uglier looking intermediate. Does anybody remember what the intermediate for these reactions were? It's got a cool name. These are these cyclic bromonium ions, okay? You don't have to know the name, but like kind of remembering that it's cyclic can be very helpful because that's going to inform you about how you're going to draw your structure here. Right, so again, these were the carbons from either side of my double bond. and they actually form a closed triangle-looking cyclic structure with that bromine. Okay? Importantly, that bromine, because it has two bonds, it also has a positive charge associated with it. So this would be the intermediate for these types of reactions here, these cyclic bromonium ions.
So it just has one of them somewhere?
Just has one what, sorry?
It just has one?
Yeah, just one of them, right? So this is going to be the first step in that reaction. The second step is that the other bromine comes along and attacks one of those carbons. In the same way that our intermediate told us something about how that HBr reaction works, right? The fact that it's Markovnikov. This actually shows us, so this is something now, up until now it's kind of been review from last lecture, this is something new. This attack of this second bromide ion, notice how it has to go around to the other side of the carbon, okay? This is what we would call like a backside attack or a anti-addition. All right, and for the most part, if we just have like a normal old alkene like this, it's not going to play any sort of a role in the stereochemistry. But if we have a cyclic alkene, something like this, we have this reaction. I'll draw the full mechanism here. You don't really have to have the mechanism memorized, but it explains what the next step is, right? So to be able to follow the arrows is something that's important. Kind of like to be able to read the picture. So that this bond reaches out at the same time that this pair of electrons goes over there. So this is the bromine that will end up being in my cyclic bromonium ion. Take a second and draw me that cyclic bromonium ion here. Let's make sure we all can draw those intermediates. Right, so it's this ugly looking thing here. Importantly, that bromine has a positive charge on it. And then in order to complete its octet here, how many lone pairs am I going to add? I don't remember if Owl wants you to add lone pairs to these, but let's make sure we know how many it should have. 2. Okay. And so one of the things that I can do, even before I move on here, I got one more product that I would have to draw if I'm being really good and doing like my balanced chemical equation kind of stuff. And I know that if I started out with 2 neutral compounds, I created this positively charged one. I'm going to have another one that has a charge of negative, right? It's got to balance out. We got to have conservation of charges. And that would be this other, so this was this orange bromine. That would be this other one here, which accepts that pair of electrons and becomes the bromide ion. Okay? But now the fact that this thing is going to like approach here from the opposite side is going to have some stereochemical implications. And so what I mean by that is the product that we're going to get here, so first of all, if I was treating it as before, I would draw just a bromine on either side. But importantly, because this is a ring, I'm going to have to consider the stereochemistry since it's anti that would lead to the trans conformation. How would I draw the trans 1,2-dibromocyclohexane? How do I do stereochemistry on these types of structures? Exactly, the dashes and the wedges, right? So this is like a partial credit answer here. You got the connectivity right, but you're missing something, which is this bond has to be a wedge and this bond a dash, or vice versa, right? But you get the trans product out of it because it's that anti-addition. So in addition to that first reaction wheel that I showed you that has like a summary of all the reactions here, again, we've only done these two thus far. There's a second page on that same thing. This is posted on Canvas under the introduction for chapter 3, which has like a cheat sheet about the stereochemistry as well. For the HBr one, you don't have to worry about it. No worries. There's no sort of stereochemical consideration. We don't have to worry about dashes and wedges. But for the Br2 one and some of the other reactions we're going to learn, we do have to make sure to consider stereochemistry when we have cyclics. Again, this is what we call an anti-addition, meaning that they come from opposite sides, and that's what leads to the trans configuration here. Okay? So on the one hand, we don't have to worry about that Markovnikov, anti-Markovnikov business, but we do have to worry about this anti-addition.
What makes it anti again?
The fact that you form, so it like forms this like triangle shape, and this is like pointed in one direction, which means that the only way that the other bromine can come is from the underside.
Okay.
And so it's sort of like is approaching from the opposite direction of where that exists, where that bromine, this orange bromine, is already pointing.
So like the carbon is kind of like the top of the slide, and then like it slides down to the bromine. And
So like really, if you were, so remember, let's like the geometry of these. Let me get a new thing here. I'll draw these in. These hydrogens in. Remember, this is like flat as it starts out, this double bond, because the geometry of an alkene, these bonds lay flat. So when the first bromine comes and attaches itself, it's actually like pointed up out of the page a little bit, or down below, however you want to think about it. But that triangle is actually sitting up a little bit, so then the only way that the other bromine can attack, actually let me be good with my charges, or rather the bromide, I guess, it's an ion, is to come from like the underside up the opposite side of where that other bromine is pointed.
okay.
If we get yourself like a model kit and all of a sudden it makes like a ton of sense because you see that there's this little triangle pointed up. The only way to approach that other carbon is from the opposite side. Okay? This is only something we're going to have to worry about with regard to cyclic compounds, but nonetheless, we want to know that if we start out with a cyclic alkene and we treat it with Br2, we're going to get the trans product. Okay? And again, anti specifically refers to approaching from the opposite side. We're going to see some where they approach from the same side. That's going to be another type of reaction we'll learn. But this one is opposite sides, it's anti. Okay? All right, so let's keep on chipping away at this wheel here. Now we're going to be treating it with not only bromine, but also in the presence of water. All right, and again, my product that I'm going to get, it's going to start out looking the exact same. Right, where I take that double bond, and I'm adding something to either side of it. Whoa. I'm using Br2, so one of those things is going to be bromine. But because water is present, instead of getting this like 1,2-dibromo thing, On the other side is going to be an OH group, right? And this OH group specifically comes from water here. Okay? This isn't one that we have to worry about the intermediate, or at least in terms of like what your homework assignment's going to be asking for. It doesn't ask you for the intermediate, but it is that same cyclic bromonium ion. The bromine actually attaches first, just like when we had our normal old just Br2 by itself. Okay? The things that are important about this is we have this Markovnikov business, which really means that the OH group is going to go in a particular place. So in this case, it's the OH group that's always going to go on the more highly substituted carbon. Okay? So in the same sense as when we had HBr, it was the bromine that went on the more highly substituted carbon. When we have Br2 in the presence of water, it's the OH group going on the more highly substituted carbon. And it is another example of an anti-addition, meaning that we get the trans product. Okay, so let's like make a little cheat sheet of what we've done thus far, all right, in terms of the reactions that we've covered. We had HBr. These are all addition reactions, so I guess first I can just say addition of alkenes. With the reagent HBr, we had to worry about what we called that Markovnikov, which is the bromine on the more highly substituted carbon. We got to know it has that carbocation intermediate. And again, we see the charge on the more highly substituted carbon. But for this one, we had no stereochem to worry about. All right, you're not going to get like the cis or the trans product, or you're actually going to get a mixture of both. For Br2, we didn't have any sort of Markovnikov business to worry about. We did have to know about that cyclic bromonium ion intermediate. All right, a triangle with the bromine at the top. But now we have to worry about the fact that it's an anti-addition, which means that we'll get the trans product for cyclic alkenes. and then the last one that we've covered thus far is Br2 and H2O. Markovnikov because the OH goes on the more highly substituted carbon. It's actually got that same cyclic bromonium ion intermediate, which is what leads it to be an anti-addition, which gives me the trans product for cyclic alkenes. All right, so here's sort of our master cheat sheet of what we've covered for each of these reactions so far. Cool? All right, let's just do a boatload of examples here. We're just going to focus on drawing products for right now. so let's tackle this first one. I'm gonna make it a little bit smaller to save myself some room here. Okay. One thing I learned about teaching chemistry over the years is you kind of teach into like different groups of people within the same classroom because everybody kind of has like just different natural inclinations. Some people are more like math, science minded, other people are just not. That's just how the world works, right? Some people can look at it and see like, all right, I see what's going on here. And other people are like, what the hell, what are we doing? And those people tend to focus much more on the process, which is why when I'm like doing these products, I'm gonna have like the same sort of process here, right? And by that I mean I'm gonna take my alkene, what I started with, I'm going to get rid of that double bond, and on either side I'm going to replace it with single bonds, right? And I can have this same strategy for every single one of these reactions here to sort of start things off. The difference is going to be what I'm adding to either side, right? Again, there shouldn't be any more or less carbons in your structures, right? We're not losing carbons, we're not gaining carbons, we're not switching which carbons are bound to which, right? So those are pretty easy errors to make that we want to make sure that we're not doing here. For HBr, what am I adding? An H and a Br, right? The question is which goes where? This is this Markovnikov one, meaning that the bromine has to be on the more highly substituted carbon. So this orange carbon here is secondary. This blue carbon here is primary. So it's going to go on the secondary carbon. For Br2, what am I adding? Just bromine. And now I don't have to worry about it because it's the same thing, right? So boom, boom, done and done. All right, and this one's probably the weirdest one that we've done so far. Br2 and H2O. I'm going to be adding a bromine and an oxygen, an OH group, and importantly, the OH group has to go on the more highly substituted carbon, right? So to be clear, Markovnikov does not mean bromine goes on the more highly substituted carbon all the time. Okay, what a Markovnikov means is that there's a specific place that you put a particular group. In this particular reaction, it's the OH group. In the HBr reaction, it's the bromine. It just means that there's this specificity to the reaction. Okay, it doesn't tell you that it's always bromine or something like that. The other thing about these reactions that drive beginning chemistry students nuts is like, what the heck happened to this other bromine and this other hydrogen? Right? I didn't draw like this balanced chemical equation. The truth is that the other product that you get is HBr, but in organic chemistry we're really lazy and we only care about what's happening to the carbons. So we often omit what we would call the inorganic products, the ones that don't have carbon and hydrogen. So I don't really care about this HBr at all. All I care about is what happens to my alkene here. Okay, so this is something that you're going to see over and over again, is just the omission of these like inorganic products that are also formed. If we were drawing a nice balanced chemical equation, we would absolutely include HBr on the other side as well. But again, we really just care about what's happening to the alkene. So that's why we, generally speaking, you will only see the organic product drawn. Okay? All right. So now let's do it for this cyclic alkene here. Again, I'm going to look on either side. I'll use the same coloring. My double bond here. I'm going to start with our alkene that we started with. Get rid of that double bond. And we have to put single bonds on either side. So remember, so this is where counting carbons is really important. You don't want to lose this methyl group, right? That's something that people it's an easy mistake to make, is to accidentally forget that particular carbon when you're drawing one of your products. This methyl group has to stay there throughout all my reactions. Okay, so again, that's when just going through and counting carbons real quick is a really easy double check to make sure you haven't made a stupid mistake. Okay, and then which carbon is the bromine going to go on, the orange one or the blue one? gotta be the orange one, the more highly substituted one. That orange one is a tertiary carbon compared to the blue one, which is just a secondary carbon. Now, with Br2, now all of a sudden, because this is a cyclic alkene, I'm going to have to worry about stereochemistry. And by stereochemistry, I mean cis-trans business, right? So importantly, the way that this, I guess I shouldn't say cis-trans, but rather EZ. But anyway, I'm going to have to make sure that when I add my 1-bromine, the other bromine is in the other type of bond, right? So if one of them I draw a wedge, that means the other one has to be a dash. All right, and importantly, if I'm being really good, that means I also have to turn this methyl group into a wedge as well. It can't also be a dash, right? You can't have them both pointed in the same direction. And I could have switched which one I decided to be a wedge and a dash. That isn't the important part. What's up?
So I switched it. So would the methyl group be a dash then on top?
Yeah, so if you had given me that would have been perfectly cool as well. All right, importantly, these two bromines have different types of bonds. If one of them's a dash, the other one has to be a wedge. All right, and then for this last example here, kind of like worst case scenario here, because this one is both Markovnikov and anti. So that means I got to put one of these two groups in a specific place. What am I going to add to the orange carbon? The OH group. So the OH group is going to be added to the more highly substituted carbon. And then the bromine is going to be in a dash or a wedge type bond. Dash, right? It's got to be the opposite of whatever I made that OH group. Okay, so this one was Markovnikov. This one was anti. But now this last one is both Markovnikov and anti. So I got both of those considerations here. Again, this is only relevant because I started out with a cyclic alkene. All right, let's do one more here in our remaining time. Very similar to the one that we did before. So which one of these two carbons is more highly substituted, the orange one or the green one? Who thinks it's the orange one? Who thinks it's the green one? Who thinks it's a trick question? It is indeed a trick question. They are both secondary carbons, all right? So what do we do there? Remember, the whole preference of the Markovnikov was because one was more highly substituted than the other. If that's not the case, if they are both equal, then you got to draw both products. Right? So in this case, the correct answer would be both where the bromine's on the green carbon and where the bromine's on the orange carbon, because there's no preference. One of them is not more highly substituted than the other. So you're going to get an equal mix of bromines joining the green carbon and bromines joining the orange carbon. All right, so then let's apply that same logic over here to our last reaction. All right, again, we got no preference going on here. So the OH group, I'll have one product where the OH group is on the orange carbon and another product where the OH group is on the green carbon. All right, we could have done it with Br2 as well, but because of the symmetry, I would just get that one product. Where bromine's on the either side. All right, so for these ones, we got two products. For Br2, we're adding the same thing to either one, so if I swapped them, it's not like I would get a different molecule. So that for this one, I still only have one product. Okay? So this actually finishes off everything we need for the halogenation reactions, that assignment on AL. The other thing I'll say is it's a really good, look, I was a college student once as well. I understand the instinctual college student urge to put off the homework assignments until the day before they're due. But truth be told, you will get so much more out of it if you at least start the practice after hearing the lecture, right? That's how you're going to make it sink in. You don't have to finish the assignment. You can always save it till later or whatever. Again, you can do them as many times as you want, right? But anyway, starting the practice after you hear the lecture is going to be really beneficial in terms of retaining the information. Because as soon as it gets to be like 2 weeks old, you're like, what is it even asking me? I don't even know anymore, right? So anyway, just a piece of advice. And yes, so I'll have office hours from 10 to 11 in 275, just science 2 right up there, okay? If you want to see your quizzes, stop by. Otherwise, they will be passed back on Monday. Yeah, have a good one. Yeah, you too.
You said to go to the testing center?
Yep. Yep, do you know where it is?
You said about Taco Bell.
It is. So hold up, I have